my talk. And also I'm very glad that so many people came to my lecture. The point is that during the program, my lecture should start 30 minutes later, because there is written that it starts from 12. But I think it's not only for my lecture, but all lectures of the conference. You see? So we have to fix that. The third lecture started 11:30. Very nice. The title of my talk is Multilinear Quantum Lie Operations. What does it mean, quantum Lie operation? I can give very short definition. A quantum Lie operation is a polynomial in free skew primitive variables. Which is skew primitive. This is very shortly, but the idea, the philosophy of this definition is the following. If we consider the classical situation of Lie algebras, then of course we know that there exists just one fundamental Lie operation. This is Lie bracket. This Lie bracket has an interpretation like the bracket of xy is xy minus yx, and in this way, this is related to associative algebra. It is well known the characterization of Lie polynomials in terms of coproduct. This is so-called Friedrich's criteria. So inside of free associative algebra, we can consider Lie algebra generated by variables with respect to Lie bracket. And then there appeared all Lie polynomials. Each Lie polynomial can be considered like derived operation in class of Lie algebras. And Friedrich criteria says that each such polynomial is a primitive element with respect to coproduct defined on free associative algebra. This coproduct in free associative algebra is defined by this formula on the variables, where inside of GI is 1. And so in this case, all Lie polynomials are primitive in this sense. And so certainly there is one basic Lie operation, but there are a lot of derived Lie operations which are precisely the Lie polynomials. Now, in the field of quantum algebra, there was defined so-called Drinfeld-Jimbo quantizations, and these Drinfeld-Jimbo quantizations, they are related to Lie algebra. Certainly, this is some deformations of universal envelope algebras of finite-dimensional semi-simple Lie algebras. And in that structure, all of them are generated by skew primitive element. So instead of this GI, there appear group-like elements. These group-like elements satisfy this commutation rule with the main variables. And here there appear some parameters, PIG, which define this the law of commutation. In classical situation, if we would like to preserve our intuition, all GI is 1, and so there is no PIJ are also equal to 1. So what is interesting to fix that in place of the primitive elements, there appeared skew primitive elements. It is interesting to note that defining relation of quantizations are also skew primitive. So somehow they are defined by quantum Lie operations, all of this quantization of the Drinfeld and Jimbo. There is equivalent approach not to consider classical Hopf algebras, classical coproduct, but instead we can consider braided categories. Instead of this GI and this PIJ, we can introduce the braiding in this way, and in this way the polynomials became primitive. but the formula of product is differ, and it is absolutely equivalent to this approach when we consider Hopf algebras, classical Hopf algebras, instead of the Hopf algebras in braided categories. And what is, I will, a few words about what does it mean Hopf algebra. Hopf algebra, this is precisely the algebra where we also have coproduct. Coproduct is a homomorphism from algebra to its tensor square. The product we can interpret like a homomorphism from the tensor square to this space, to this algebra, and coproduct is dual notion, and if there is product and coproduct and they are related by some axioms, then we have Hopf algebra. So free associative algebra can be considered like Hopf algebra, while considering all generators like primitive, and then since delta must be homomorphism, we can calculate the value of coproduct for any polynomial. So this is the situation is the following. Instead of the primitive generators, we consider skew primitive generators. And as you wish, you can take the braided case, but we will orient it mostly on this situation. And then quantum Lie operation is nothing more than polynomial in free skew primitive variables, which is skew primitive. Very important thing for these operations is the following. If you would like to define some Hopf algebra by means of generators and relations, there is a very unpleasant situation that the intersection of two b-ideals is not a b-ideal. And so we cannot do this directly in the classical situation, that if we have some relations, we cannot consider the minimal b-ideal, which define the Hopf algebra, defined by these elements, by these generators. But if the polynomials are skew primitive, then indeed we can define, because each ideal is b-ideal if the ideal is generated by skew primitive elements. So this is another reason there is some duality for these skew primitive elements. So our problem now is very clear. We have skew primitive generators. We have these n-squared parameters, which define this commutation rule, and these n-squared parameters completely define all the structure of polynomials. And our problem is described to find something which looks like Frederick's criteria, describe all skew primitive polynomials. If it's possible, certainly to find one basic polynomial which generates all others, something like this. This is the starting point. Okay, let us try to resolve this problem for n equal to 2. This is very simple. We have x1, x2, we have this delta of x1, this is delta of x2. We have to multiply these two tensors, and we have 4 terms. This term is trivial, it always appears, doesn't matter what element we have here, we will have this term. And this term is also somehow trivial, because no matter what we have here, we will have here the same element, and these all group-like elements. The most important part... This one? No. x1, x2, g1, g2. But they are commutative. They act like by diagonal, so G commutes. But I still... Ah, yes, you're right. Of course. Thank you very much. I will correct this formula. Certainly, yes. Yes, G1, G2 must be here, and x1, x2 must be here. They're not commutative. Left and right, they're not. G1, G2 commutes, x1, x2 not. But the tensor also doesn't commute also. Thank you very much. That's right. So this part is more important. We have delta 0. We denote this part. We take off all the skew primitive part, and our problem is to find when this part is equal to this is back. So I just here to repeat that we define this delta zero in this way because this u multiplied by 1 and gu multiplied by u, this is in proper way, proper tensor. And so we consider this part. This is skew primitive part. If delta zero equal to 0, entonces this is skew primitive polynomial. So our problem is to resolve this problem, delta zero of u equal to 0. So our problem now is to discuss when this sum is equal to 0. Here we have x2, x1, so they are generators, they are linearly independent. So we must suppose that this one equal to 0 and this one equal to 0. What we have? No, not yet, sorry. Because here we consider just delta of x1, x2. We have to do the same for x2, x1. Change just indices 1 and 2. So we have this expression. And certainly here appear the coefficient alpha. So we can see the arbitrary multilinear polynomial of degree 2. We can suppose that one of the coefficients equal to 1 without loss of generality. And so we have this problem. We have here this element, we have here this element. Both of them should equal to 0, and the result is very nice. We have brackets, x1, x2 minus p12, where p12 is defined by the commutation rules, x2, x1, and we denote this like operation in two variables, but there appear a condition, p12 multiplied by 2 or p21 equal to 1. If we equate this 0 and this 0, we can find alpha, and the determinant should be equal to 0, so we have this condition. It is interesting to note in this point that if we take the situation in braided category, this condition, if we suppose that this condition is always true, we will get the condition that tau squared is identical map. This means that the braiding is involutive, tau squared equal to 1. Or if we consider the situation with colored Lie algebras, so we will take this relation alpha gh multiplied by alpha ag equal to 1. This is precisely the condition by means of this condition, by means of B character alpha, is defined color Lie superalgebras. And this condition which defines the so-called generalized Lie algebras defined by Manin and Gurevich. And also there is nice theory, and so this is precisely related to the situation. If we postulate that this polynomial is operation, is skew primitive, then we get these conditions which define the situation in terms of braided categories. So let us go ahead. The case n equal to 2 is completely considered. Let us introduce, first of all, this skew commutator, which is uv minus some coefficient multiplied by vu, where p we defined like a B-multiplicative map. So for the generators, this is just PIG, n squared elements, and these n squared elements defined the value of p for any polynomials. In this way, p of uv comma w, this is has this B-multiplicativity condition. And from this side also. So in this way, p is defined for all homogeneous polynomials, and so for all homogeneous polynomials, we have this bracket. Yes. here.
Okay, so the way you define the alpha in the next slide.
Well,
The alpha depending on G and H. Can you also show that the alpha is additive in each one?
Yes, of course. And this also tau, if we, if we define here what does it mean braiding, then we have this bilinearity, precisely. Now let's turn to the case n equal to 3. We have to do the same. We have take x1, x2, x3 to calculate delta 0. We have 6 terms, and here will appear some polynomials in PIG. If instead of ordinary tensor you will put here braided situation, then they will appear the same coefficients, in fact. Okay. Now arbitrary multilinear polynomial in 3 variables has this form where alpha p runs, where pi runs through the permutation group of 3 indices. So what we have finally, we have to resolve this equation that this sum equal to 0. We have 12 equations with 5 variables, or 6 projective variables if you wish, but always I suppose that one coefficient is 1. And we have 6 parameters. So it looks not so easy for the moment to easily resolve this, this equation. We have 12 equations and 6 variables. In general, if we put arbitrary n, then we have n factorial multiplied by n minus 1 equations, n factorial minus 1 variables, or n factorial variables, if we consider them like projective, and n squared minus n parameters Pij. So we have to discover lots of symmetries. If we have no symmetries, certainly we have much more equations than variables. So as I told, it is not easy to, certainly this is not transcendental problem to resolve these 12 equations with 6 variables. We can analyze this system, but it is a little bit routing calculation, not so nice. So let us make some theory in order to resolve this problem in proper way. Let us define, introduce left and right primitive polynomials. We need primitive, but we will consider left or right primitive polynomials. We fix some variable, x1 say, and consider a polynomial, multilinear polynomial, which is linear in each of the variables. And then certainly we can calculate delta 0 of w. We have the summation. And if it's occurred that ai are independent of x1, then we say that w is left primitive with respect to x1. Since w is multilinear and coproduct of the variable has this very nice form as a skew primitive element, then these polynomials ai and bi are multilinear, and x1 will appear in this part or in that part. So if it occurs that a1 are independent of x1, then we say that this is left primitive. Right primitive certainly is absolutely symmetric. If bi are independent, all of them are independent, key should be a, no e. We start with investigation of these left and right primitive polynomials. it's absolutely clear that if we take left primitive and right primitive polynomial, then it must be primitive. Because in any tensor, x1 should appear from the left or from the right. And if it doesn't appear in that right and this side and this side, then so certainly this is Q primitive. By this reason, it is very important, it's very reasonable to investigate left primitive element. Proposition 1, W is left primitive and x1 if and only if W has the following representation. Some coefficients, we have n minus 1 coefficients, which can be arbitrary. And here we have long skew commutator. First element is x1 and another the rest of the variables. I recall that the polynomials are multilinear. So this is the theorem, the proposition 1, which explain what type of polynomials will appear if we consider left primitive polynomials. Proof, how to prove this theorem. If n equal to 1, then certainly delta 0 of x1 is always 0, x1 is always q primitive, this is right primitive, and so we have this equality, and left, right, and right, we have trivial commutator. x1 is trivial commutator, x1 with empty set of variables. Okay. Certainly we can start with n equal to 2, but then we need to do some calculations, but this is more simple to start with n equal to 1. Now suppose that u is u as left primitive polynomial. Then delta u has this form by definition such that ui are independent of x1. And di depends on x1. We have this representation. In this representation, we have to write the commutation rule. The j is equal some coefficient. This is u is small letter. This is not certainly this is capital letter, but it is in indices. This is index p. Which depends on u and j, xj, multiplied by j multiplied by u. This is commutation rule, nothing more. But what is important here, appear this coefficient. Then what we shall do? We have to calculate delta of this q commutator. We write this q commutator, apply delta like homomorphism. Fortunately, here appear precisely the same coefficient. Then we develop the product once we know what is delta of u. This is delta of u by this element minus p multiplied by the product on the vice versa. And now we can drop all elements which are all tensors of this form where ui are independent of x1. What we will have here, it's very easy to see that xj, j is not equal to 1. J is greater than 1 because polynomials are multilinear. And so we can analyze where px1, and we have these two terms, and then commutation rule has the same coefficient, and so the one term will cancel, and we get this relation, which means precisely that this commutator is left primitive. So all long commutators are left primitive. This is very nice. Now we have to analyze why vice versa. See, if we have a left primitive element, why it has such representation by long skew commutators. To analyze this situation, let us take some left primitive polynomial. This polynomial can be written in this form, alpha multiplied by u, where alpha is coefficient. And here we have the linear combination of another words. W this is polynomial, and this is a leading word. We can order all words in lexicographical order, and we suppose that x1 is greater than x2, etc., is greater than xn. And among all the words, all monomials which appear in W, we can find the leading one. So we have this representation. And we analyze two cases. First, when W starts with x1. So W has this form. Then we can do the following trick. We can consider the difference W minus alpha multiplied by this long skew commutator, this one. And what is very important, that the notion of left primitivity is linear. And so the linear combination of left primitive elements is left primitive. And so this difference is also left primitive. And we get element W prime, which is left primitive. What we should fix in this decomposition, if we develop these skew commutators, then we will see that the leading term of this difference is less than W. Why? Because W starts with x1, and all words which appear here will start with another letters. And the word W will cancel, because here we have alpha, and here we have alpha. So we can apply the induction, because the leading word is less than W. We produce induction of the leading word. Case B, suppose that W do not start with x1. So W has this form, ux1v, and u is not equal to empty word. Then we should analyze the coproduct of the product. Coproduct of the product of skew primitive elements. If we develop the product, if we substitute the binomials in each one of the xn, then we will get the following sum. The summation by all subsets of the set 1 to n, which appeared in the following way. What does it mean, WA? WA, this is some subword of the given word, but some word which appear from deleting some of the letters. And WA appears from this word when instead of the variables, we put the group-like element, G, chi A. And so in this way, they are put in different places. And if we would like to move all group-like elements in one side, then there appear some coefficients which depend on the Pij. But in this form, there not appear the coefficient, but the variables and group-like elements will appear in some way. Now we have to analyze when a tensor G multiplied by U tensor V appears in the decomposition of delta of W. And the statement says that it happens if and only if W is a shuffle of these two words, U and V. What does it mean, shuffle? If we take two words, we can move these words from one side to another, just jumping letter by letter. And all words that will appear from these two words in this way, they are called shuffle of these two words. And nothing more. So, for example, if we have a word AB and word XY, then the shuffles are in this way. AB, XY, then X goes, and B goes there, and so on, and so on, and so on. Okay. Now we are going to prove, in fact, that if W starts with element with a letter other than x1, then the W majuscula is never left primitive. This is not our idea. So so we have that delta of W, don't the W is the leading word, has a tensor gx1v multiplied by u, because W is a shuffle of two these words, x1v and u. If we move u totally in the left extreme position, we will have u x1v. This is precisely W. Therefore, this element will appear. All other shuffles of x1v and u are greater than this element, because we know that x1 is greater than xe, and so if we don't move all of the u, then x1 will appear before than here, and so all of them are greater. And it implies that no one of the words wi, which appear in the polynomial, is a shuffle of these two elements. It means that when we consider delta of wi, this tensor will never appear. And it means that this tensor will not cancel. And it means that the polynomial W majuscula, capital W, has this term, and here this part depends on x1, and so this is not left primitive. This remains uncancelled. This element remains uncancelled in the delta W majusculus capital, so that W is not left primitive in x1. And our proposition is proved in tonos with all the details. Symmetric proposition. W is right primitive in x1 if and only if W has this representation where instead of the commutator, skew commutator that we have discussed before, we just modified it a little bit. Instead of the coefficients PUV, we take PVU minus 1. In fact, it is easy to see that it has this representation in the in terms of the brackets which we introduced before. How to prove this theorem, this proposition? I will not repeat because arguments are absolutely equal. There is lots of ways. For example, we can consider antipode and then just apply the proposition 1. And also we can repeat all the arguments. So this is not the fantastic problem, but certainly we have the dual theorem, dual proposition, which has this form, that right primitive elements has the same representation with respect to modified brackets. Very nice. So let us introduce these polynomials, d sub u. This polynomial corresponds to a word E1, E2, E3, I2, I3, IN. This is word. So, this is a polynomial which has coefficients which are depending on Pij. If we develop this brackets, then we have the polynomials du. Okay, now theorem. This is the end of our small piece of theory. Each linear dependence of that polynomials, this is fixed polynomials, they may be linearly dependent, maybe not. And the theorem says that each linear dependence of that polynomials define a quantum Lie operation which has the following form. BU defines the dependence of du, and so we have this equality, certainly, if instead of du we put this polynomial. And the theorem says that this is precisely skew primitive polynomial, quantum Lie operation. Inverse statements is also true. All quantum Lie operations have this representation. All quantum Lie operations have, there is another mistake, have this representation. It means that if we have some multilinear skew primitive polynomial, then there exists linear dependence between these elements, and the very polynomial has two representations. In this form, like left primitive element, and this is like right primitive element. How to prove this theorem? It's very easy from proposition 1 and 2. If it is skew primitive, then it is left primitive. It has this representation. If it is skew primitive, this is right primitive with respect to x1. So we have this representation, and this is the same polynomial. But probably BU are another coefficients, BU prime. But we can analyze words which that start with x1. And we see that the sum of all words, the linear combination of all words which appear here and start with x1 is precisely this linear combination when there is no brackets. And in this side is the same, there is no brackets. And this equality of these two polynomials means that BU is equal to BU prime. So immediately we have this representation from proposition 1 and proposition 2. And conversely, if we have this equality, then this part say this is left primitive, and this part say this is right primitive, and if it is right and left primitive, this is skew primitive, nothing more. So this is, in fact, corollary of the two previous propositions. Some very interesting consequences. In fact, here we also have a lot of equalities. For example, let us analyze the words that are ending with x1. No, how to get here the word which is ending with x1. We have to change the order x1 and xi2. Then we have to change completely this part from this and so on. So each long skew commutator produces just one word which ends with x1. And this is also the symmetric word which appears from here, and with some coefficients. Certainly there appear some coefficients. Here also we have symmetric word, the same word, with another coefficients. If we analyze the coefficients, we have these coefficients. So we have at least n minus 1 factorial equations between p, I, j, if there exists at least one skew primitive polynomial, just one quantum Lie operation. And fortunately, this is very surprising, that all of them are equivalent. N minus 1 factorial relations are equivalent each other. And I didn't put here the relation. Here it is. It is. So all of them are equivalent to this, that the product of all Pij, when I is not equal to j, is equal to 1. So we will call this condition like existence condition. This is for existence of quantum Lie operation, this necessary condition. How much time? 10? 20. Okay, thank you very much. So this is the existence condition, but is it really existence condition? Well, I will say that this is existing condition, so we will not prove, but I will formulate the theorem which say that if this existing condition is valid, then really exists at least one quantum Lie operation. Nice. Let us take the case n equal to 3. N equal to 3. The polynomial dx2 x3, we have two polynomials, 2 factorial. It has the following form. It is easy to develop the brackets, and so we have this form. dx3 x2 has this form. If the existence condition is valid, then we have this equality. We can develop the product, and this is easy calculations. We'll show that we have this relation. But what does it mean, this relation? This relation means that determinant of this matrix is equal to 0. And so it means that they are linearly dependent. And what are the dependencies? Certainly it's easy to find the dependencies unless we have here 0. We have to analyze what happened if P31 multiplied by P13 equal to 0. And if not, then we have the only quantum Lie operation, because there is just one dependence. And what happens if P31 by P13 is equal to 0? No, first of all, let us remember that in the case of two variables, x1 and x3, we have that this is also existence condition. There exists the binary quantum Lie operation. And this binary quantum Lie operation can generate the operation in 3 variables, precisely like in Lie algebra, we can consider superpositions. And so we have at least 2 quantum Lie operations. But the theorem says that the number of linear dependencies are in 2 polynomials and not more than 2. And so we can not have more than 2 variables. So in this detailed analysis, it doesn't matter. Now we can suppose for simplicity that the denominator is not equal 0. We have just one operation, and it has the following form. We have just one quantum Lie operation. If we have existence condition, is suppose for the moment that the denominator is not equal to 0. Very nice. Let us turn to the case n equal to 4. What we have now, what can be our hypothesis? If n equal to 2, we have just one basic operation. This is commutator. If n equal to 3, we have also one basic operation. So how many quantum Lie operation? How many quantum Lie operation we can expect if n equal to 4? So we have a sequence. 1, 1. What is the third term? Who can guess? 1, 1. 1, 1, 1. Okay. This is precisely what I thought. So by using the theorem, we have some system of linear equations. We can make some tricks without details. So we get, in fact, finally, the system of 6 equations with 6 variables, with these coefficients. Coefficients are defined in this form. If we have a word on Pij in this form, we can define another word, just change all the indices, because this is double indices. You consider this difference, A minus A bar inverse. So for the simplicity of notation, I have this matrix. Before there was 12 equations, there are some symmetries, so we reduce here. It doesn't matter. What is important, that this is absolutely symmetric. I cannot do anything, but still, since we weight one operation, we can suppose, this is homogeneous system of equations, so we can resolve this. Suppose that one variable is parameter, and so to resolve these 5 equations. But this is a little bit routine work, and certainly I tried it to to find some trick, don't to make all the calculations. I didn't found, and so I decided one day, okay, I just would like to look to the eyes of this on these operations, and I will make all the calculations. So I started and worked various days, and then the result was fantastic. 0 equal to 0. It was the solution of this system of equations. But what does it mean? First of all, it means that I didn't make mistake, because if you make mistake, you have 1 equal to 0 normally. Then, what happened if you have this homogeneous system and the result is 0 equal to 0? It means that the rank of this system is not 5, as we were supposed. The rank is not more than 4. And we have 2 arbitrary elements. We have at least 2 different solutions. But if we have the rank is not 4, then we have cut 2 of lines and 2 of columns, and we get the 4 by 4 matrices. And certainly you have here lots of zeros. And the resulting matrix is triangular. So in 3 minutes, I got the solution. So what is this story is interesting? The hypothesis means a lot in the solution. If from the very beginning I suppose that there are 2 solutions, so in 3 minutes I resolve this system. And if not, so it's much more complicated. And the triangle system, it's very easy to resolve. Certainly we have to make some calculation, we have to verify that everything is good, and so on and so on. But this is not so complicated. So we get 2 solutions. This is, I write this, one of them. And how to find another one. It is interesting that the indices 3 and 4 are, play the same role, and we can change 3 and 4, the indices 3 and 4, here also. And in this way, we just replace these indices and we can find the second solution. Now another question. So we have a sequence 1, 1, 2. What is the fourth one? 3. No, 1, 1, 2, 3. Okay, just intuition. The numbers of Fibonacci, yes? 1, 2, 3. Yes, but still the answer is not. Here the answer is n minus 2 factorial. Here. So the answer is the system which appeared there has n minus 2 factorial solutions. Okay, step by step. First of all, first theorem says that there exists a non-zero multilinear quantum Lie operation in variables x1, x2, xn, if and only if this existence condition holds. The product of all parameters equal to 1, just one hyperbolic condition. And so we can work in this hyperbolic surface. There exists a principal generic quantum Lie operation. This is also interesting thing. What does it mean? Principal generic quantum Lie operation. Why it's principal and there exists some principal operation. The situation is the following. Let us look to this existence condition. If we apply symmetric group to the indices, just change the name of the variables. We have n factorial ways to rename the variables. Oh, excuse me. For example, like when we introduced the notion of left primitive elements, it was related to x1. It may be related to x2, x3, and so on. So we have some logical symmetric. It doesn't mean that Sn, the symmetric group, acts on the coefficients Pij. Because probably P1, 2 equal to 1 and P2, 1 equal to 2. And so we cannot replace them by means of the authomorphism. But nevertheless, there is logical symmetric. If we have some statement which is hold for given variables x1, x2, xn, then the same statement is valid for xp1, xp2, xpn. So we have at least n factorial statements without any jobs. So we have this way. Now let us take the quantum Lie operations. We have found n minus 2 factorial of them, and let us consider one of them and just replace some variables. Certainly we will get another operation. So what does it mean principal generic? First, what does it mean generic? Let us suppose that variables satisfy just this condition, but not any more relations between PIG exists. Then certainly in over the field which is generated by these variables, there exists the quantum Lie operation, at least one. And among them, we can find just one operation such that all of them will appear just changing the name of the variables. By means of linear combinations, certainly, because the space of the operations is linear space. And so there exists one of the operations such that the changing of the n minus 2 variables, not only two, we will get the basis of all quantum Lie operations. So it means that there exists a principal quantum Lie operation. There exists n minus 2 factorial symmetric generic multilinear quantum Lie operation. The notion of symmetric quantum Lie operation is opposite. It means that here, if we change the variables, the names of variables, we will get absolutely another operations. But, for example, the quantum Lie operation ordinary, if we change the order of the variables, we will get the same operation multiplied by some coefficient. So this is precisely the definition of symmetric operation. Symmetric operation. So we suppose, we do not suppose that if the variables here is free with these relations, then certainly we can apply the action of the symmetric group. And the theorem says that there exists n minus 2 symmetric generic multilinear quantum Lie operations. So there exists n minus 2 factorial operations which are symmetric. Each one of them is symmetric, so we cannot generate another ones. If we consider not free variables related by this relation but arbitrary, then there is some, the number of polynomials is greater or equal to n minus 2 factorial and less or equal to n minus 1 factorial. And one open problem. If the dimension of the space of all multilinear quantum Lie operations is greater than this minimal value, then all of them are old. In which sense old? The point is that if we have quantum Lie operation, we can consider them like operation. We can consider superposition of these operations. And so if we have an operation which is superposition of the operation of the less order, I call here this operation like old. And so this is the hypothesis which is open still now. Who are interested in more details of this branch of the development, I published the book Quantum Lie Theory, lecture notes in mathematics, Springer, and thank you very much. But I have here one of these books, and what I would like to present it to our.
Thank you very much. Thank you very much.
Feliz cumpleaños. Thank you. Thank you.
Questions?
This means, at least in some cases, do you know what is it like as SN module?
No, this is precisely the investigation of these symmetric operations and generic operation. This is like this model, this investigation.
Dimension of that White House module.
I didn't investigate this, but it's likely that this is the same space. White, yes, but it's still interesting. This is applied to this open problem. That's right.
basic question. When you deal with, for example, a 2x2 matrix with entries in a non-commutative algebra, and you want to define something like the determinant, so it's not like AB minus BC because so is your commutation rules that you have at the beginning, can they be used to say, for example, try to define the
Determinant.
in a
Well,
2x2?
Well, I didn't thought about this, but this is very interesting question because you know this is quantizations of Lie groups. They have some type of these matrices in order to define quantum groups, but not the deformation of Lie algebras, the dual situation. And so this is very interesting, but I didn't thought about this. There is general theory of Kohn, of the inverting or investigation of this determinant and so on. But this is too general. I think something specific may appear in this way. This is very interesting question also.
Another question? Let us thank the speaker again.
Thank you.